All right. So, so let's say I have ABC, right? And I ask the same question, how many ways can you arrange the letters in this word, right? How would you go about it? Well, I mean, these are just three letters, so we can always choose the harder way, which is that, we list each possibility, right? Hello.
Yeah. Yeah, I
Yeah.
can hear you.
Okay, okay. So this is what we can do, right? These are the basically number of possible arrangements for ABC, or you could have also thought about it as cab. Like if I had replaced this with cab, it would be the exact same question, right? However, the issue here is that there are these repeated letters, right?
Yeah.
Okay. So you might have studied how you dealt with those. So I'm gonna, for example, do a particular example here, just thinking about this, and then you can easily solve this one as well. So for example, let's say I had instead of B, instead of C, I had a B, right? Which is basically identical to this thing, right?
Yeah.
Similar actually. So what are now the number of possible arrangements that I can make? Well, that would then be just A, B, B, right? B, A, B. What else?
BBA.
Yes, B, B, A. Okay, fine. So these are three, right? That's
Yeah.
it. Now, if I replace in this uh, in this grouped set, if I replace B with C, what do I get? A, B, B, right? B, B, A, B, A, B,
Mm.
A, B, 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 A, B, and B, B, A, right? So what's happening actually? These are my correct number of arrangements if these are my letters, right?
Yeah.
And if they were completely distinct, I would get this. Now, if simply I'm just doing one thing, which is that I'm replacing the C with the B, and I get this. What this tells me is that I am double counting in this set, right? So ABB, I'm double counting this. Likewise, BBA, I'm double counting here. Likewise, BAB, I'm double counting here. So this is basically supposed to be just counted once. This was also supposed to be counted once, and this was also supposed to be counted once, right? Which are basically this, and this, right? So
Yeah.
what that means is that it's three factorial, which are the normal number of ways, given that they were distinct. Just like here, this was basically 3 factorial, right? Once you get a situation where you have repeated letters, what you do is you just divide it by the factorial of the number of repeated letters. So here, if you divide 3 factorial by 2 factorial, you get 3, which is the correct number of possible arrangements for ABB. Does that make sense?
Yes.
Okay. So now, how would you go about doing this?
10 factorial over 3 factorial because S, T, and I are being repeated.
Okay. So 10 factorial over 3 factorial. No, but that's the thing. Here, the f- the reason I wrote down 2 factorial was that b was repeating 2 times. If it were, let's say, b b b b, right? Then I'd write 3 factorial here. And
Oh,
then
okay, okay.
4.
So it will be 10, got it. So it will be 10 factorial over 3 factorial times 3 factorial times 2 factorial.
Very good. Precisely. That is exactly right. Good.
All right.
All right. So now the other question is, if all arrangements are equally likely, what is the probability that two i's are next to each other? So it's basically asking that, given that you have two i's, right? Two i's together, what's the what is the probability of you getting two i's together, basically?
Okay.
So I want you to spend some time, and I'm gonna, in the meanwhile, uh, pause this. Uh, Let me do it another way as well. You are absolutely right about the first, like the probability, the second part, right? So,
Okay.
yeah, hold on. Where was, yeah, here. So you've done part of it, right? Which is that you've basically calculated the number of ways in which you would get two i's together, right?
Yeah.
But what the question is asking is a little bit more. So the
By the
question is
way, yeah.
asking, yeah, please
See
go
the
ahead.
screen now.
Okay,
Oh,
okay,
I was just about to say that you aren't sharing your screen, but now it's visible.
okay. So the other thing is that the prob it's asking for the probability, right, of two i's together. So you have to divide it by all possible arrangements. So whatever you got in the A part, you divide it by the thing that you got in B part. So let me just clarify it
All right.
a little bit. Okay. So for the first part, the answer is very simple. That's just 10 factorial over 3 factorial to account for the s's, 3 factorial for t's, and 2 factorial for the i's, right? So this would give me, I have a calculator somewhere here. Yes. So 10 factorial divided by 3 factorial times 3 times 2, 50400. Okay. And what you suggested, which is the correct approach, which is that now what you do is you treat the two i's in one block as a single letter. So let's say I want to denote it by X. And what are the other remaining letters? Well, those are just S, T, A, T, S, T, C, S, right? So now I have 9 letters, right? I have 9 letters. So that would just be the number of ways in which two i's are next to each other would just be 9 factorial over 3 factorial, 3 factorial. Why am I not dividing this by 2 factorial?
Because
That's a
you're
question for
already
you.
taking them, because you're already taking the two eyes as one entity.
Yes, right, precisely. So because I mean, even here, I'm just taking one identity, right? I'm not taking two letters here, I'm just taking one, right? So what
Yeah.
this actually is the number of ways I can arrange X and then these all the other letters, right?
Yeah.
And then we know that X is made up of I and I. So, and then you divide. So this is the number of ways you get i's next to each other, and then you divide it by the total possible arrangements, which are these, right? 50400. So 9 factorial divided by 3 factorial. 1 by 5. Okay, good. I'm going to do it this and this question. I don't, by the way, uh, it's a simple method, sure, but uh, I prefer the other method, and I'm now going to solve that question in another way. Okay,
Okay.
so yeah, I find it more generalizable. So yeah, okay. So the other way is, now you have letters, these letters, right? And you want to find out distinct permutations, right? So the number of ways in which you can arrange these letters. So what I would like to think about is in these terms that you have 10 slots. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And you have these three S's, three T's, two I's, one A, and one C, right? And you want to fill these slots with these letters. Does that make sense?
Yeah.
That would be exactly the same as how many, like the answer to the A part, right? That the number of ways you can arrange the letters in statistics, right? So, what do you think the answer would be? So, let's say it totally depends on me. I can choose any one of these, right? So, let's say I choose, I mean, S is first. So, I want to select, basically, I want to choose three letters. Sorry, I want to choose three positions from these slots and put my S's there. That would be 10C3. Is that clear why that would be the case? Because from the 10 positions, I'm
Yeah.
selecting three, right? Does that make sense?
Yeah. Yeah.
Okay. Uh, okay, let me ask you this. Uh, Now these three S's are identical to each other, right?
Yeah. Yeah.
So where is my 3 factorial, like the division by 3 factorial? Should there be a division by 3 factorial?
Um. No,
Why
I
not?
don't think so.
Why not?
Because you're already accounting for the fact that जो S's हैं, they're coming in three different positions by doing 10
But
choose 3. No?
yeah, okay. No, you're right. But if I switch these, my arrangement does not change, right?
Yeah, if you mean you switch the S's, like you
Yeah,
do, yeah. Okay.
my arrangement does not change because they are indistinguishable from each other,
Hmm.
right?
Hmm.
So the way I like to think about it is that, it's actually 10p3 over 3 factorial, where this is preserving the order and this is taking into the account the repetition. Either way doesn't really matter because the answers are the same and you can always think of this as this, right? So your 3 factorial, that repeated, uh, the factor that counted for the repetition is already taken into account in the combination term. That's what I wanted to insist upon. Is that clear?
Yeah.
Okay, good. So let's go ahead. So that's 10C3. Okay, fine. So I've filled three slots and then put basically fixed my S's there. Now, obviously, they could have been anywhere. So, but I'm just choosing one representation. So this is one task that I've done. And you know what the product rule, right? So let's say you have five desserts and three main courses at a restaurant. So how many ways can you choose? Well, that's just five times three, right? You know
Yeah.
about the theorem? And I mean, it's fairly easy to see, right? These
Yeah.
are the possible number of arrangements. All right, good. So we're going to use that as well. So because these are independent choices, likewise, these are independent choices. So I'm from my 10 slots, I'm basically picking three and then putting my S's there, right? Likewise, now my remaining slots are seven. So for seven, I choose again three and put my T's there. So let's say T is here, T is here, and T is here. Again, for my two I's, now my options are, what should I write in this term?
Four choose two.
Yeah, precisely. What would be the next term?
One choose one and one choose one.
Two choose one, right? Because when I
Oh
filled
yeah.
it with my I's, I had two slots
My
remaining.
bad,
So from
yes.
two, one for A
And then one
and
choose one.
one from one, right? Make sense?
Yeah.
Okay, good. Another way you could have also thought about it is that, okay, you know what? I don't want to do this. Fine. So let's say I want to put my eyes first. Then that would be just 10 choose 2. And now 8 remaining, 8 choose 3. And then again 5 remaining, 5 choose 3. And then 2 choose 1 and 2 choose 1 choose 1. The answers would be
The same.
same, right? Because it should not matter which spaces I occupy first, right?
Yeah.
And with which letters. So, yeah. So the product rule is at work here, and all of these are your distinct choices. Okay. Likewise, so when you calculate this, it's going to give you the same answer as the one that we got before. So I'm gonna do this one because I haven't tried it. So 10 choose 2, 8 choose 3, 3. Precisely the same answer. Okay, good. Now the other thing would be, uh, now when I do this, right? How would I go about it? Well, first,
We
I'd have to, yeah,
we've done this part.
we have done this part, but I'm doing it another way, which is like
Okay.
I was doing a part in another way. So I also want to carry on the same method onto part B as well. Okay.
All right.
All right. So how would we do that? Well, first of all, what do we need? We want to calculate the probability that the two eyes are next to each other. So for that, we need the denominator to have two eyes, right? Only then would we be able to place them together, right?
Yeah.
So what are the number of ways uh you can put in two eyes together? Sorry, in two eyes in these 10 positions. You know the answer to this. A simple, what are the number of ways, right? Let's say you have just from these slots, you want to choose two slots and then fix your eyes onto those slots. What would be the mathematical representation of that? 10 choose 2, right?
Okay,
Because
yeah.
from the 10 slots, you just want to choose 2. Where is the information about eyes encoded? Well, it's gonna be encoded here somewhere. I mean, they could have been any letters, right? But we don't want those letters. We want this letter. So we're gonna fix our eyes, right? So that this would
Yeah.
then be 10 choose 2, that's 45. And now these are all of these are equally likely, right? So I could have placed my eyes here, here, or anywhere else, right? So 45 of these arrangements. This is going to be my denominator because it has two eyes, right? And now the numerator, I want to ensure that my eyes are next to each other. So what are the number of possible ways? Well, then they can be here first, like this, like this, like this, and this, and so forth. And there will be 9. This would give you 1 over 5, exactly as before. Make sense?
Yes.
Okay, good. Uh, Now, uh, how about you attempt question number 2?
All
I
right.
would, uh, uh, yeah, spend some time on it. I'm gonna pause the. Okay, okay. So, I want to specify two things. One is rank, and the other, I always forget this. So let me just see my notes. Suit. So your ranks are basically 1 to 13, where, I'm donating 13 with king, right? And your suit is basically sorry, spades, the four suits, spades, sparrow, I think, or no, clubs,
Clubs, yeah.
clubs,
Hearts and
hearts,
diamonds.
and diamonds. Yeah. So these are your suits. These are your ranks, 1 to 13. Okay. And now you have basically five, six basically cards, right, in your hand because you're considering this and you want to show that you have two two pair, right? So means that you have pair of one rank and then another pair of another rank, and then the remaining are different. And likewise, three of a kind is just uh three cards have just one rank and the other three have different ranks. So yeah. When the meeting ends, it will immediately restart. So you'll have to join it again.
Okay.
What do you think is going to be the starting point?
So I found the probability or the possibilities rather for the first two pair wala part, and it's 14,040. Is that correct?
It's a prob. So
No, I mean I
14,000.
just found the possibilities. And 40. What I did was, okay, 13 choose 1, times 12 choose 1, times 10 choose 1, times 9 choose 1. Sorry, it should be times 11 time choose 1. Yeah.
Okay, so let's do that. Okay, the meeting is gonna end, so I'm gonna just start it and the other one. I'm just gonna stop it and then just immediately start it. So you can join it.
Okay.
Yeah. Okay.
With the same link, right?
Yeah, yeah.